Welcome to today's chemistry lecture. In this lecture, we are going to study the third concept of this chapter, which is change in temperature during a chemical reaction, and the other topic, factors affecting the rate of reaction. So, let's start our lecture with the first concept, that is change in temperature during a chemical reaction. We will study step by step and point by point. So the first concept on change in temperature during a chemical reaction. Chemical reactions are quite often accompanied by changes in temperature. These changes indicate whether a reaction is exothermic or endothermic. So let's look upon exothermic reactions. Definition: reactions in which heat energy is released into the environment. How we observe? Observations: the release that is absorbed by surroundings, causing their temperature to increase. It means the container will feel hot. Let's see the real world example. The reaction of quicklime with water. When quicklime reacts with water, slaked lime is formed and a massive amount of heat energy is released. Chemical equation will be quicklime plus water converted into slaked lime plus heat. Now see the endothermic reactions. Definition is reactions in which heat energy is absorbed from the surroundings. Observations are: because heat is drawn away from the surroundings, it causes the surrounding to cool down. For example, the container will feel cold. Real world examples: by dissolving ammonium salt in water. When ammonium chloride or ammonium nitrate is dissolved in water, heat energy is absorbed, causing the reaction container to become noticeably cold. Means the container will be cold when the reaction will happen inside the container while reacting the ammonium chloride or ammonium nitrate with dissolving the water. There are some general rules of temperature on reaction. Rate acceleration. Regardless of whether a reaction is exothermic or endothermic, increasing the overall temperature of the reaction system increase its rates. The 10 Celsius rule. For many common chemical reactions, the rate of reaction doubles with every 10 Celsius rise in the temperature. Means when we rise the temperature with 10 degrees Celsius, the rate of reaction will be doubled. Practical application means cooking. Cooking food utilize high temperatures specifically to the speed up the chemical reaction that break down the chemical component of food, rendering it edible and digestible much faster. For example, when we speed up the heat, we will cook fastly than the normal heat. Let's move forward to the next topic, which is factor affecting the rates of reaction. According to the Klein theory, any factor that changes the total number of successful effective collisions per second will directly affect the overall rate of a chemical reaction. It is the concept that we will learn in the first lecture of this chapter. So, the effect of concentration of reactants. First, the phase requirement. In order for a reaction to occur, the reactant particles must physically come into contact with one another. Means reactants will be react with each other physically. Because of this, reactions are most efficiently carried out in a single phase. Means such as entirely within liquid solution or entirely in the gas phase. When the reactants share the same phase, their particles meet easily at the molecular level and collide with minimal effort. Other factor is concentration dynamics. A high concentration means there is a high number of reactant particles per unit volume. Means This increase in particle density creates higher chances of effective collisions, which result in a higher rate of reaction. Mean direct relationship, increase in the concentration of reactants is increase the rate. A decrease in concentration will decrease the rate. It is directly proportional to the reactants. As we increase, it will increase. If we decrease the concentration, the rate of reaction will decrease. So, concentration dynamic is where the higher number of reactant particles per unit react with each other to make product effectively. For example, here we have two experiment scenarios. For example, combustion of coal and limestone. With at low concentration, how will they work, and at high temperature, high concentration system, how will they react? In lower concentration system, in air, 20% oxygen persists relatively slow. In higher concentration, in pure oxygen, 100% oxygen proceeds rapidly and vigorously. As we see limestone, at lower concentration system with dilute HCl reacts at a slow controlled rate. At higher concentration system, limestone with concentration of HCl react at a fast and rapid rate. It means the combustion of coal with pure oxygen has a much higher concentration of reacting molecules per unit volume than atmospheric air, and limestone will react higher concentration of acid particles, increase the collision frequency against the limestone surface. Hopefully, you will find this chapter easy to understand. See you in the next lecture.